Welcome to this lecture series in linear algebra. In this lecture, we look at the notion of dualizing a linear map. We've previously looked at how to dualize a vector space. Here we look at the notion of dualizing a linear map. So let us recall what we need. So of course, we will need the notion of dual spaces. So for a vector space V, the dual of V is written this way, and it is defined as all the linear maps from the vector space to the base field. And we have discussed this many times. Then there's this notion of dual bases. So if we have picked a basis for a vector space V, then the dual basis is a basis of the dual of V and is defined as follows. So this is the notation, and the definition is Vi star of Vj is 1 if I equals j and 0 otherwise. Right, so that's the definition of the dual of a given basis. And we will need the notion of the annihilator of a subspace. So if V is a vector space and S is any subset, any non-empty subset of the vector space V, then recall that we defined the annihilator of S as all those linear functionals which kill every element of S. And we noticed that this is a subspace of the dual, and we also derived this fact that if W is a subspace of V, so this time it's a subspace, not just some subset, then the dimension of the annihilator of W is the difference of the dimension of V and the subspace, the dimension of the subspace. Okay, so we will use these facts, and with that, let us proceed. Here are some problems for practice. And now let us get started. So we will define the notion of the dual of a linear map. The terminology that is standard is transpose. Somehow we do not call it the dual, but the idea is really dualizing the linear map. So let me define it. Fix a linear map from a vector space V to a vector space W. The transpose of T, or if you want, you can call it the dual of T, is a map from W star to V star. So you take the dual of the target and make it the domain of this guy, and take the dual of the domain and make it the target of this guy. So it kind of is going in the other direction. So the dual of T, or the transpose of T, is a map of this sort, which is defined as follows. So you pick some functional on W, and we need to prescribe what does this guy do to this thing. So here is how it happens. Let me draw a diagram and explain. So we have the linear map T, which is from V to W. Now G is a functional on W, so G is a map of this sort where capital F denotes the base field. So we can compose them. And once we compose them, this will be a linear map because it's the composite of these two linear maps. This is nothing but that guy, and this is what we define as the image of G under this map. So this map we have defined as the map which sends G to this guy, G composed with T. This is the dualizing map, or this is the dual of T, or the transpose of T. Let me write it. This is the transpose of T. Okay. Further, you can expand out by saying that T transpose of G, it's really that thing. What does it do to a vector in V? Now this is legitimate because this is a functional on V, and therefore you can feed a vector from V to it. What is it? This is equal to G of TV, right? So I'm just kind of restating this definition in a somewhat different way. All right, and here is a small exercise. Check that. T transpose is a linear map. Very, very simple exercise. Okay, so what we have done is, from the space of linear maps from V to W, we have created a space of linear maps. We have created a map to the space of linear maps from W star to V star. Right? We had a map here, call it capital T, and that became the transpose of it. So let's call this map tau. So tau sends T to T transpose. Right? That is the map tau. That is what we have done essentially above. And more interestingly, you can check that tau is also linear. Tau is a map from a linear space to another linear space, or as we call it, a vector space to another vector space. And it is thus legitimate to ask if it is a linear map, and it is indeed a linear map. Okay. Yeah, I don't think there's any problem here, because there shouldn't be any problem. So this is a linear map. All right. So let's see a very simple example. Suppose we have a subspace of a vector space V, and we have the inclusion map from the subspace to V. So recall what is the inclusion map. So if we have a subset of a set X, nothing to do with linear algebra. If we have a subset of a set X, then we can define the inclusion of A into X as simply the map which takes little a to A. So that's the inclusion map, and that's what we have here. And of course, this is a linear map, right? So we can ask, what is its transpose? Now, by definition of the transpose is going to be a map from the dual of V to the dual of U. And we need to figure out what this is. So then this is, we need to fill in the blanks. So let's figure it out. So for something in the dual, we have this thing is equal to that thing by definition of the transpose. But this is nothing but the restriction of F on U. So F is a map from V to the base field, but this is as good as the restriction of the map F to U. U is in particular a subset of V, so you can restrict a function on V to the subset U, and you denote it this way. So the transpose of the inclusion is restriction. So this is the map. It takes a functional F to the restriction of F to U. It's a very, very simple example, not very illuminating, but it helps. Okay. So now let us talk about the kernel and images of the transpose, and in particular the rank and the nullity of the transpose. So fix a linear map from a vector space V to a vector space W. Then we claim that the kernel of the transpose of T is the annihilator of the image of T. So we can express the kernel of the transpose in terms of the annihilator of in terms of the linear map T itself. So this is not at all hard, the proof of it, but the consequences are what are of importance. So how do we prove this? Well, if G is in the kernel of the transpose, this happens if and only if, by definition of the kernel, that is the case, which happens if and only if this thing kills all vectors in the vector space V, right? T transpose of G is an element of the dual of V. So this is 0 if it kills every element of the vector space V, which by definition of the transpose is same as asking G of TV is 0 for all vectors V. So here I should have written for all vectors V, which, note that, is same as saying G annihilates the image of T. So this is the step that you need to note. It is not a hard step. G is killing everything that is of this form, that is of the form T of V for some vector V. That is as good as saying G kills everything that is in the image of T, which is the same as saying this. So G is in the kernel of the transpose if and only if G is in the annihilator of the image of T, and that is same as saying this statement. So we have proven this, and as a corollary, we see that the rank of the transpose is same as the rank of the original map. Why is this? We just use the rank nullity theorem. We have rank of transpose of T is the dimension of the domain of T transpose, which is W star, minus the nullity of the transpose of T. So what we have done is we have used the rank nullity theorem on T transpose. Okay. But now by the previous proposition, this is equal to dimension W star, or well, before that, let's just use the definition of the nullity. The definition of the nullity is, so let me make this small correction. There is no meaning to the phrase dimension of nullity. Nullity is already dimension of the kernel. So rank of T transpose is dimension W star minus nullity of T transpose. Now, what is nullity of T transpose? It is the dimension of the kernel of T transpose. Okay, but now by the previous proposition, it is equal to the dimension of the annihilator of the image of T. All right, but so before we continue, let me, instead of dimension W star, let me write dimension of W, because the dimension of W is same as dimension W star, so I can erase that star. And now we use the fact that the dimension of the annihilator of something is the difference of dimensions of the parent where this lives and the dimension of this. So what I'm saying is this is equal to dimension of W minus dimension of W minus dimension of image of T. Why is that? Again, this lives inside W. This is a subset of W. So dimension of the annihilator of this subspace is dimension of W minus the dimension of the subspace, which is the image of T. So we have this, but this is equal to the dimension of the image of T. And this is by definition the rank of T. So the rank of the transpose is same as the rank of the original linear map. That is quite interesting. Okay, so now finally we will show that the image of the transpose is annihilator of the kernel of T, which is in symmetry with the previous lemma. So before we, or rather in the proof of it, first we will note. So first note that this containment holds. Right? So why is this? It's a simple deduction. You start with something in the image, and you pick something in the kernel of T. Right? We want to show that basically to establish this containment, we just need to establish that G of V is 0. So that is what we want to do, but since G is in the image of transpose of T, say, I shouldn't have called it G, let me call it F. F is better. So we want to show f of v is 0. And since f is in the image of T transpose, say f is T transpose of G for some G in W star. And now f of v is T transpose G of v, which by definition of the transpose is equal to G of T of v. But since v is in the kernel of T, this is G of 0, which is 0. And that proves the containment. We have shown that this is contained there. Now, to establish equality, it is sufficient to establish that the dimension of this guy is same as the dimension of that guy. And that will follow from here. Or maybe we will also make use of this. Let's see. So what is the dimension of this guy? This is same as the rank of T transpose. So we just need to show that the dimension of this guy is also the rank of T transpose. But what is the dimension of this guy? Let me not write it, let me just say it. What is the dimension of that guy? The dimension of that guy is dimension of wherever kernel of T lives, which is V, minus dimension of kernel of T. Right? But this is equal to the rank of T. But we know rank of T is same as rank of T transpose, as we just discussed. So rank of T transpose is equal to rank of T transpose, and hence these two dimensions are equal. And this containment therefore establishes that this equality holds. This containment is actually an equality because the dimensions of these two things are equal. So that's the proof. So let me just say ... and you can fill in the details. I've said it in words. Okay, so let's continue. So now we will talk about the matrix of T transpose. So again, we have a linear map from a vector space V to a vector space W, and fix a basis capital B for the vector space V, and fix a basis for W right. Once these two bases are fixed, one can form the matrix of T, and to form the matrix of transpose, we may take dual bases. So let B star be the dual of the basis B. So this is the dual basis which we recalled in the beginning. And C star be the dual of C. Right? So this is a basis for V star, and this is a basis for W star, but B star is actually the dual of B and C star is actually the dual of C. Okay, so here is the fact. So fact or theorem if you like, lemma maybe. The matrix of T, so yeah, so say that the matrix of T with respect to these two bases is, let's say, the ijth entry is Aij, and it is going to be an M cross N matrix. All right, so then the matrix of T transpose with respect to dual bases is, just flip the indices. So that's what this is, but let me explain this in a simple way. So suppose the matrix of T was of this sort, A, B, C, D, E, F. So it was a 2 cross 3 matrix. So if this were the matrix of T with respect to the two bases, then what would be the matrix of T transpose? The matrix of T transpose would be this thing. That would be the matrix of T transpose. So that's what this theorem is saying. And the proof is routine, just follow the definitions. Nothing, no ingenuity, no creativity, nothing is needed. Just follow the definitions. It's a good practice to prove such things. The definitions actually sink in once you do them. Okay, so that's the matrix of the transpose. If you know the matrix of the original linear map, you can easily calculate the matrix of the transpose. So this is all that I wanted to discuss in this video. As usual, like, comment, share, subscribe, and I will see you next time.